All right, welcome everyone to the video here talking about weak acids. Okay, so we're in our discussion of what makes something a strong acid, strong base, weak acid, weak bases, right? So in this video we're going to talk a little bit about what are weak acids, what is the properties of weak acids and such. So a weak acid is an acid that does not fully dissociate in solution. Okay. Right, so often in strong acids we use this, just arrow right to the right to indicate a strong acid fully breaks apart in solution, okay, and completely donates every single proton, okay. But a weak acid will often use this equilibrium arrow, right, to indicate that it's not going to fully break apart all of the acid, right, that there will be some HA in solution, but there will also be A minus and then H3O plus, right? So this reaction does occur, but it doesn't go to completion, and it establishes an equilibrium between the acid and its conjugate base, right? So here, again, as a reminder, right, HA is our acid, right, and A minus is our conjugate base, okay, right? And so what are some of our weak acids? So there's a lot of weak acids, right? Anything that's not a strong acid is a weak acid, right? Now here I'm giving some examples of weak acids. A lot of the examples here I'm giving are kind of carbon-based acids, alcohols, and things of that nature, right? And to kind of show you, right, that often, okay, things like benzoic acid, acetic acid, we'll deal with a lot, right, often are written in this way, right, where you have this OH at the end, okay, OH here, right, OH here, okay. Note that's indicating, right, that hydrogen is bonded to an oxygen, okay, right, which is good, the hydrogen is bonded to oxygen because the hydrogen can then break apart to form the conjugate bases, okay, right, listed here. But just keep in mind that the OH itself is not going to break apart. Okay, OH is not breaking apart. I'm not going to have CH3COOH break apart into CH3CO plus or something like that, right? It's going to donate a proton, not a hydroxide. Okay, so while it looks like, like HOCl has an OH that could donate, right? It's not going to break that oxygen-chlorine bond, okay? But it will break the oxygen-hydrogen bond, okay? And so these are proton donors, so these are all acids, but they're all weak acids, okay? And then they have their conjugate bases, right, listed there, okay? Right. Right. Often for these type of acids, again, the acidic hydrogen is not written at the beginning here. It's not written HC6C5COO. It's written, right, as C6H5COOH because this is how it's bonded, right? The hydrogen is bonded to the oxygen here, so we write the hydrogen next to that oxygen to indicate it's bonding, okay? And again, it denotes a proton, not hydroxide. Okay, so when you see molecules like this, these are weak acids that donate protons, not weak bases that donate, say, a hydroxide ion or something. Okay. So, right, as mentioned, right, weak acids establish this equilibrium reaction, okay, right, which means it has an equilibrium constant, right? So we call the equilibrium constant for a weak acid dissociation reaction Ka, okay? This is, again, just a normal equilibrium constant, Ka, that we talked about in chapter 15. We're just giving it the subscript A to indicate it is for a weak acid dissociation, right, reaction, right? And so, right, we're just dealing with a weak acid dissociation reaction, right? And so for these reactions, you can, again, write it with water to write it with H3O+. Often I'll write it in this way. I'll just say it's HA dissociating to H plus A minus, okay? Which has an equilibrium constant, okay? for the first reaction written in that way, second reaction written this way, right? And so again, I'll often use this version of the equilibrium constant, which again we call Ka to just indicate it's referring to a weak acid dissociation equilibrium. But again, it's just an equilibrium reaction, right? Equilibrium constant, products or reactants raise their stoichiometric coefficients. Right, and so what does Ka tell us about our acid, right? Well, when we talked about equilibrium, right, we talked about how the larger the equilibrium constant, the more the reaction favors the products, right? And so what that means is the larger Ka, the more, right, your acid dissociates, right? So if I have a weak acid HA, right, equilibrium H plus plus A minus, right? The larger the Ka, the more I favor my products, right? So that means the more this acid dissociates, right, the stronger the acid is, right? The more it dissociates means it's a stronger acid, right? The strongest acid you can have is a strong acid which fully dissociates, okay? Right? While the smaller the value of Ka, right, the more of the weak acid molecules are still left in solution, and the weaker your acid, okay? Right? So the larger Ka, stronger acid, smaller Ka, weaker your acid. Okay? Right? And in terms of percent ionization, okay, which is defined, right, it's the concentration of what's ionized over the original concentration, which is basically just the concentration of H plus at equilibrium over the original concentration of HA, right? Right? The larger the Ka, stronger acid, the larger percent ionization, right? That's what we're talking about. Okay. And finally, talk about polyprotic acids, okay? So, right, polyprotic acids, H2SO3 here, right? Notice if I look at the Ka, right, here I have Ka1 and Ka2 indicating, Ka1 is indicating the first hydrogen that's removed, okay? And then Ka2 is indicating the second hydrogen that's removed, right? And you notice the value of Ka gets much smaller, right, as I go from removing the first to the second, okay? For acids with 3 hydrogen ions that can be removed, right? The third acid dissociation equilibrium, right? Ka3 is going to be even smaller, right? Right? Each proton that you remove is going to become more and more and more difficult to remove, okay? So it's become a weaker and weaker and weaker acid, right? So that's what we talk about with the strong acids. H2SO4 is a strong acid. It will fully break apart into H plus plus HSO4 minus, okay? But HSO4 minus is a weak acid that has a weak acid dissociation equilibrium reaction, right? Given here, right? Which will have some Ka value, which will be less than 1, right? So this is a weak acid, right? And it's just because it gets harder and harder to remove a proton for every subsequent proton you're removing in a polyprotic acid.